Yeah. Okay, here we go, friends. Put every other distraction away, whatever that might mean. Okay? We're so close to fall break, friends, I know. Okay, our first property we're going to talk about is the property of boiling. Now, with all our properties today, we need to think at the molecular level, okay? Once again, there's no math when it comes to intermolecular forces, right? It's all about visualizing. It's very heavy on that side of our triangle of what is going on at the molecular level, okay? So have a picture, even if the picture is a bunch of circles. That is often how I visualize atoms, as bouncy balls, okay? Because I don't know, when I was younger, I collected bouncy balls. I really liked them. I don't know what they all are now, but that's like just any picture is better than nothing, okay? So first off, when you are visualizing boiling in terms of chemical property is actually the point at which the vapor pressure, okay, vapor pressure is the pressure of the liquid pushing up, is equal to the external pressure, which is just air pressure pushing down. Okay, so in this beaker of water, okay, all I have to do to get it to boil would be to remove all the pressure from above, and it would boil, right? Like that's why water will boil in space. It's because there's no pressure pushing down. That has nothing to do with the temperature. That water boiling, I could drink because it's not actually hot. It's just come to an equilibrium of pressure. Now, why we link temperature to boiling is, what do you think, if I move these molecules faster, why is it able to boil? Stephen?
Because they can act against the forces of the
Yeah, right. They now have more energy to push against the pressure pointing down. Okay? But you want to think about boiling not so much in terms of like hot, right? Because some things boil like liquid nitrogen, but it's not going to burn you, it's going to freeze you. Right? So don't link so much always boiling means hot. Boiling is just a point at which we're going from a liquid to a gas because it's overcome the pressure putting down. Okay? Another example is water on top of Mount Everest boils at like 70-something degrees because in higher elevations, there's less pressure pushing down. Yeah, AJ?
My brain just froze. So with pressure, does that like mean that with high enough pressure, water would solidify, or does it remain liquid because it expands when it's frozen?
So if I'm understanding what you're asking, AJ, and if it's not, let me know. So like liquids can be turned into solids by increasing pressure. Yeah.
So can water do that, or
Mhm.
does it remain liquid because it increases in size when it becomes solid?
Because it starts limiting their movement, because really it's about movement, right? Remember, solids have very little movement, liquids more, gases lots, right? And pressure would start limiting their movement as well. So I believe so, but I've actually never thought, like, that's how we make dry ice, is by pressurizing the CO2 in the air. I want to buy one of those so I can make my own dry ice. But you literally just pull carbon dioxide from the air and then pressurize it into the cubes, is how it's made.
How does it avoid also like making dry oxygen, dry?
Oh, like how do they, I don't know exactly how they purify it in the process of pulling it out, but there's some way that it does, some sort of filtration that it does that separates it. Good observation though, Mary. Yeah?
So could we go on a field trip to Mount Everest and then drink room temperature boiling water?
Oh, brilliant.
It wouldn't be, because I'm 72 Celsius, not Fahrenheit. Good clarification. But right after fall break, I'll put this water in a vacuum chamber and we'll boil it here, and then you can drink it right after.
Wait,
Once you take it, it boils for like a few seconds, but like it literally will be boiling, and you can pull it out and drink it.
sounds awesome. Wait,
I know it's not as cool as going to Mount Everest, but yeah, Gavin.
My dad actually tried calculating the temperature, like what temperature water boils at here, because we're like.
Oh yeah, because it's not exactly 100.
It's close to like more like 2 or 3 degrees.
Oh okay. So like I think it's like 98 something Celsius. So yeah, because in Utah it doesn't boil at that higher temperature. Yes, Mary.
we have a vacuum chamber at school.
I have one. It's like small, like it's like I don't know. It's a tube. What's this called? A case?
A box.
A box? Looks looks fancier than a box, but a dome, yeah, it's a dome shape. And then it has I hook up tubes to it to a vacuum pump, and then it can vacuum out all the air. Yeah, cool.
To what extent could we use this vacuum chamber in class? Like, what could we use it for?
So we'll use a variety of things, because next lesson's all about gases, is where we're transitioning next to, because we're gonna now talking about liquids. So we'll use it for a variety of things, actually. So, okay, fill in this blank for a smiley face. Ready? I'll fill in the first one, you fill in the second one. If something has strong IMS, so the strong intermolecular attractions, what would that mean about its boiling point? Don't say it out loud, but just fill in the blank. Your answer should be either mean higher or lower, are your two options. Strong IMS are going to equate to higher or lower boiling points. Don't say it out loud, just write your answer. Okay, on the count of 3, you're going to point up if you say higher, point down if you say lower. Ready? 1, 2, 3, point. If you're pointing up, have a smiley face because you're correct. Can someone give me a sentence that maybe explains why that is? Why would having strong IMS equate to high boiling points? Go ahead, AJ.
Because it makes them sort of a lot harder to pull apart and actually become a gas.
Yeah, right? It's all about, right? Think of our little waters we had last time, right? IMFs are all about positive and negative attraction, right? And the tighter that attraction is, well, then it's going to take more energy for it to break apart, right? The better friends that Brinley and Chloe are, right? If they're really good friends, it's going to take a lot to break them apart. But if you're not really good friends in general, then it doesn't take much to pull them apart, right? Like, you know, like Brinley, like Michelle, she's always really sad when it's random seed day because she has a strong intermolecular force with her friends, right? She wants to see with them, okay? All right, another smiley face. This one you can talk to your table with. Circle, which would you predict to have a higher boiling point? Okay, I'm going to give you their Lewis structures because you should think about that. Okay, so water, carbon tetrachloride is just a tetrahedral.
I say HEO.
Okay, 1 minute, decide and circle your answer.
And also water.
Wait, so does water have the one that has like what's the
Oh, hydrogen bonds? Yeah, hydrogen bonds? Yeah, they Sorry, I'm just getting all the stress out.
Okay, everyone point at the ceiling. Point at the ceiling, everybody. All right, if you're picking water, point to the cupboards. If you're picking carbon tetrachloride, point to the window. 3, 2, 1, point. Water would have a higher boiling point because what IMS does it have? All 3, right? It has hydrogen bonding, dipole, and London. While carbon tetrachloride, what forces does it have?
London.
Only London. Make sense? Okay. All right, next property is surface tension. Surface tension is pretty much what the word is describing, right? It's a tension at the surface of a liquid. Okay? Alright, so the way I visualize surface tension at the molecular level is I kind of think of it as like a game of Red Rover, right? Where all the molecules at the surface are holding on to each other, right? And that ability to break it, okay? If something, don't say it out loud, do this one on your own. If something has stronger IMFs, what claim can you make about its surface tension? Is it going to be a high surface tension or a low surface tension? it again.
Chlorine dihydride, or no, dihydrogen fluoride, would that be like,
That doesn't exist, does it?
no, you're right, my bad.
You're good.
FH, so, would that be liquid at room temperature?
It's hydrofluoric acid. I'm not positive. It has a really, like, I know it turns to a vapor really easily, but I think it is a liquid, but it does evaporate. Okay, point up or down, depending on what you put on your blank. Ready? 3, 2, 1, point. Good. Yep, if something has high forces, it's going to have a high surface tension. Can someone give us a sentence explaining why at the molecular level? Yeah, Cameron, go ahead.
The stronger the bonds between atoms in molecules, the stronger the bonds will hold on to each other in surface tension.
Perfect. Have a smiley face for that. Okay? Right? Red Rover idea, right? They're holding tight, and it's going to be a high surface tension. Right? If they're not really holding that tight, then it'd be a low surface tension. Okay? All right, talk to your table. You got 1 minute. Maybe only 30 seconds this time. Circle which one between water and our carbon tetrachloride again would have the highest surface tension.
Definitely water. Because the hydrogen bonds breaks.
Talk to your table. Make sure you agree. That way, if you get it wrong, you'll at least be united together. Feels better to be wrong with others.
Have you ever seen the difference in surface tension between alcohol and water? Have you ever seen those videos?
Videos of like water, but not.
It's kind of like it's
We did this in one of my
obviously
science
there's
classes.
others underneath. The idea is kind of like the fact
We saw if we could balance a paper clip on
Right.
the surface of water and on the surface of like rubbing alcohol. You can balance the paper
a
clip
little
on the
bit more
water.
stagnant versus like underneath. They don't get as
Also,
locked
if you like
into,
drip it onto a penny,
the grabbing onto
you can get like
Oh, I've seen that.
multiple milliliters of water.
due to somewhat of the fact also like
Alcohol, you got like 3 maybe.
But yes, you're right. There is still tension in it. It's just not something we can measure. And so that's why when we can measure the surface tension, like there's a way to actually measure that. I don't know. I'd have to review my physics. But yeah, that's kind of why we can't so that measurement can only be described at the surface level versus the rest. Does that make sense? But you're right. Like they're still holding on under, like they're under. Okay, point at the ceiling. Point at the ceiling, everybody.
Oh, I did.
Okay, point to the covers for water, point to the window for carbon tetrachloride. 3, 2, 1, point. Well done. Yep, it would be water due to the fact it has more IMFs holding it together, right? That is the pain you feel when you belly flop into a pool is because of the hydrogen bonding in it, right? Okay, questions on surface tension? Yes, Steven?
So if the atoms are holding each other together at the surface, why not at like other points?
Yeah, the same question Mary did. They're still holding underneath too. The difference is surface tension is just an actual measurement we can take. Like scientists have a way of measuring surface tension, but it doesn't in a sense because we're not being able to measure what's underneath. But yes, it is still in a sense the ones underneath are still being held together in a similar fashion.
Okay.
Yeah, Cameron.
Is this why we do the whole water on the penny, like dropping water onto a penny until it breaks? That's like measuring surface tension.
Yeah, that's one way in a sense you can see the surface tension difference. Yep, is like the droplet formation. Yep.
Is this also why, like, we have to have, like, we have to have a spacesuit in space because if we don't, then the water in our body boils?
The idea of pressure, yes. Yep, is that because there's no air pressure pushing on you,
You'll just decompress.
then you, not, what's the opposite? Explode, I guess, because everything would want to turn to a gas.
Motion explode.
So, okay, next definition here is vapor pressure, okay? Now, the term vapor, everybody, vapor simply refers to something in the gas state that normally is a liquid. So water, when water evaporates, we call it water vapor. We don't really call it water gas. Even though like water gas and water vapor are really the same thing, but that's where we use the term vapor. Okay, versus yes, like oxygen doesn't exist as a liquid at room temperature, so we call it oxygen gas. But it really is, it's just in that same state. Okay, what vapor pressure is vapor pressure, first off, has to be in a closed system. So the word closed there is indicating it's sealed. So if it's not sealed, then there's no pressure because it just leaks out. We'll talk a lot about pressure next time in our gas lesson, but for now, think of pressure as force of collisions. Okay, the more collisions you have with the walls of a container, the higher the pressure is going to be. Okay, so the harder they hit and the more often they hit, the higher the pressure. So vapor pressure is if you have a sealed container, some of that is going to evaporate. The pressure of that evaporated state is the vapor pressure. Yeah, AJ.
The definition says when the liquid and vapor are in dynamic equilibrium. What does that mean as opposed to like static equilibrium?
It technically means that all the time molecules are going back in, but as one goes in, another comes out. So the ratio never changes, but it's not like those molecules only stay in the vapor state. They are trading with each other. Does that make sense? Yeah, good question. Okay, so this right here, it's kind of before and after, but if this was one picture and this was another, this would be high vapor pressure because there's a lot of molecules to collide with the walls, and this would be very low vapor pressure because there's very few. Steven?
So the liquid or whatever will evaporate until the pressure is so high it can evaporate?
Yep. It reaches a point of where it just stays at a set amount. So it doesn't continuously evaporate in the closed system. Okay? All right, fill in the blank here on your own. Okay? The stronger the intermolecular forces would mean what in terms of its vapor pressure? So you're putting either high or low again on that blank. Make a prediction. And then we'll check it. Okay? I would rather have you make a prediction that is wrong than just wait for me to tell you the answer. Okay? Because you learn a lot more from mistakes than just waiting. Set your pencil down if you're done thinking. So I can give people their time if they need it. Okay, make a fist. On the count of 3, point up or down. If IMFs are high, what does that mean about vapor pressure? 3, 2, 1, point. This one is inverse. If something has strong IMFs, it would have a very low vapor pressure. Can someone give us a sentence at the molecular level? Help us visualize that. Go ahead, Gavin.
The molecules in the liquid would hold together better, so they just want to escape.
Yeah, right. If they're holding strong here, then they're not gonna go there.
Oh.
Right? And so that means you would have less of a vapor pressure. Everyone see the connection now? Okay, for another smiley face, circle. Which one's gonna have a higher vapor pressure, water or carbon tetrachloride? You can talk to your table now.
The fancy word.
Circle the one.
I think we just have to get new notebooks.
And every time you've done it, yes, every time.
Yeah, I'm not arguing.
It's like
Or it's like not even
how is that still?
This paper is deceptively heavy.
yeah, this one is you. You weren't thinking about it Yes, sir. Is that- Okay, point at the ceiling. Point at the ceiling. 3, 2, 1, point. Is it water or carbon tetrachloride? Water is the cupboard, carbon tetrachloride is the window. 3, 2, 1, point. Very good. You're pointing at the window, have a smiley face. And by the way, every time we have pointed with our finger in a direction, if you got it right, you got a smiley face. So I think what, that's up to 6 now?
Yeah.
Today?
3, I need 2.
Okay. All right, let's take a look at some example AP questions when it comes to intermolecular forces, and then we'll talk about our last properties, okay? This one we're gonna do together, and then the next one I'll have you try with your tables. So, I'm gonna kind of talk you through how Miss Alviso would solve this problem. Okay, keep in mind that a lot of AP questions, it's a problem-solving process. It's not a read and I can answer, because it's you have to connect here to here, and then here to here, and then you can get the answer. Okay, so our question says 4 different liquid compounds in flask are represented above. The table below shows identifies the compounds. Flask C shows the most particles in the vapor phase. Based on the data table above, make a prediction of which substance is in flask C. So my brain would say, all right, when I look at this picture, what property is being shown here?
Vapor pressure.
Vapor pressure, okay? So I'm focused on C, and it has the most particles. So I'm going to say, okay, I know that this has a high vapor pressure.
Therefore, it has a low boiling point, right?
Good. Well, I'm going to do an in-between step, AJ. Therefore, what about my IMFs? Good. The biggest theme with IMF questions on the AP exam, they don't use the word IMF in the entire question. But you need to recognize whenever it's about a property of these phase changes, vapor pressure, boiling point, what was it what I said? Oh, surface tension, right? Any of these properties, you have to connect it back to IMFs, because that is the why. So now I'm going to come over to the data table they gave me, and they gave me boiling point. So what's the connection between boiling point and a low IMF? If something has low IMFs, what does that tell me about its boiling point? And so that tells me that the identity of my substance must be pentane, because it has the lowest boiling point, therefore the highest vapor pressure. Everyone kind of see how I problem solved that through? Okay, but like, you're doing yourself a disservice in AP chemistry if you read a question and you're like, I don't know what to do. Right? You just gotta take it step by step, right? It's like walking in the dark with a very dim flashlight, right? You just take a step and then you'll see another light, and then you take a step, so on and so forth. Yeah, let's see.
Does that mean that like class A is optional?
I would say that is a great claim. Yep. Yep, because since that one has the lowest vapor pressure, it should correspond to the highest one. Have a smiley face for that connection. Yes, Cameron?
I've heard the name octane before. What's it used for?
It's in gasoline.
Oh, gasoline.
Yeah. Miriam?
Are any of those safe to drink?
No. No, definitely not. Do not drink anything that ends in an ane. Octane, pentane, propane. Don't do it. Okay? Okay, for smiley face, this isn't on your packet because it disappeared. But I want you to answer it. Okay? Decide for me between BR2 and BRCl, which one would you predict to have a higher boiling point? You can talk to your table. Give you 1 minute. Which one would you predict to have a higher boiling point?
Oh yeah. CRC have a higher volume. This is one of those like the polar one.
Wait, Wait, Miss Alviso, the question is. Example problem.
No, that's what I'm saying. That, we're not that question. This is the question.
He's like so concerned, like, wait, what's going on?
Okay, everyone ready? You're gonna tell me your prediction of which one had a higher boiling point. Ready? Fingers in the air. We're gonna do, if you think it's BR2, point that way. If you think it's BRCL, point that way. Ready? 3, 2, 1, point. You should be pointing at the window. So why would we predict that BRCL has a higher boiling point, Mason?
Oh.
Because it has dipole-dipole attraction, it has a stronger attraction force.
Perfect. So in comparing our two forces, right? BR2 just has London. BRCL would have London and dipole forces. Have an extra smiley face for that, Mason. Okay? Based off prediction, you just use IMFs. But if they give you data, make sure you trust the data. Okay? So, same things, but now we're given information. The boiling point of BR2 is 332 Kelvin. The boiling point of BRCL is 278 Kelvin. What does it mean if this has a higher boiling point about its IMFs? This one must be stronger IMFs than that one. Yes, Cameron?
Where does Kelvin measure with Celsius and Fahrenheit?
It's like
You add
Celsius.
273 to Celsius measurement to get to Kelvin. Okay. Fahrenheit's, I don't know, 9/5 plus something.
Oh, yeah, like the, I remember one.
Yeah, but Celsius to Kelvin's easy, you just add 273. So,
Freedom.
okay. So, this is a case, everybody, I want to point out here. Everybody ready? And I've given you this answer already. This is an example of an exception. Generally, dipoles are stronger than straight up London. But last time, flip to page 6 really quick, everybody. We had a chart that compared the strengths of our forces on the top of page 6. If you look on that chart, on the far left, it has dispersion. Can you see that? Right underneath it, it says dipole. But notice, and maybe highlight that overlap region. There's a point at which dipole forces can be weaker than other dispersion forces. Can you see that overlap region? Now, you are not expected to know exceptions without given data. Okay? If it was a question before, you would have got points for saying BRCL, because we had no data to go off of. But given data, then you have to recognize, okay, this is an exception where, look at how they wrote it. Okay? The London forces of BR2 are stronger than the combination of the forces in BRCL. Now, we talked last time, what can make a London force even stronger? Londons get stronger with what? Do you remember, Leslie?
More electrons.
Like another thing where like a positive end and a negative end. So like
Good. And what's making the positive and negative in a London? Do you remember?
Yeah, it's a molecule
And they're electrons. So the more electrons you have, the greater the London force can become. And so this must be one of those cases where, and that's what this fancy word here, polarizability. Okay, this is pretty much just due to having a lot of electrons. The more electrons you have, the stronger that London can become. It's actually why bromine, even though it only has London forces, is a liquid at room temperature. When almost everything else that only has London is a gas. Iodine, its London forces are so strong, it's a solid at room temperature, right? So just be aware of that exception. They love to do this. But no, you don't have to just know it, but make sure you match the data. Yes, Karen.
It's like a dumb question, but iodine solid at room temperature. Is iodine salt? Salt is just iodine added to it. And why do we have iodized salt?
Because iodine, I exactly. But iodine is a it's an important nutrient for our body, and it's often we don't get it in other ways, and so they put iodine in it to help us. But I can't remember what for, but I know it's important. Yes, Steven.
So if
Yeah.
iodine is solid at room temperature, does that mean it has to be a solid?
Yes, yeah, they are as well. So, okay, questions on this idea of when exceptions come into play? Once again, don't ever predict an exception without data. But if you have the data, make sure you match it, okay? All right, this one's for you to try. You got 2 minutes, okay? You can talk with your table. I need a full explanation here, FRQ question. They're giving you 2 structures and they're telling you their melting points. Your job is to explain why the melting point of this is higher than the melting point of that. Ready, set, talk to your table, go.
The only difference between this one now is this one has
That one?
Hydrogen bonds.
They all have all forces.
This one has.
If you're not, I'd look at the structures and find what's different about them. Because why it's different must be why the melting point is different.
Everything has one dispersion.
this one has
But hydrogen,
Because this one has 2 hydrogen bonds. And this one only has 1.
oh, silicic acid does have, yeah.
They're pretty similar. Good, so this one has this thing on it. So I would having OH connection. What does it mean about its ions? Good, yeah. So I would having this make it have a strong force. Remember, there's a significance of OH. What type of ion? Okay, sorry, 2 minutes maybe was a little short. I'll give you a few seconds here to finish up and then we'll pick on some people to share. So whenever I have to justify a trend, right, or a pattern, right, I focus on, okay, if the melting point is higher, that must mean what about its IMFs? It must mean they're stronger. So then I look at the structure and I say, why would this have stronger IMFs than that one, even though they technically have all 3? Okay? All right, do I have 2 volunteers that want to read theirs first? Smiley face. Do you take your hand back, Eddie, or do you still want it?
yeah, I'll do it.
Okay, we'll go Eddie and then Cameron.
So both of them have the same amount of, both of them have all 3, but salicylic acid has 2 hydrogen bonds, and methyl salicylate only has 1. So salicylic acid has a higher melting point because the
Perfect.
bonds are strong.
Good. Cameron, how did you say it?
That was the same way. I just said salicylic acid is 1 more hydrogen bond than methyl salicylic. And since hydrogen bonds are incredibly strong, this increases the IMF of the molecule and makes the melting point higher.
Yeah, right? This is a hydrogen bond, but the more sites you have to hydrogen bond, the more it can be attached to one another and hold together more. Yeah, Steven?
Why does the carbon hydrogen not count as a hydrogen bond? Like it doesn't chloride.
Their electronegativity is identical.
So essentially that.
There's no shift in the because to get pot right, you need a shift in the electrons.
Whereas with oxygen.
Because the idea, right, is that the electrons get pulled away, creating the positive and negative side. So,
Yeah.
did that answer your question?
Yeah, I think my question was bad, because I kind of already understood.
Did you answer it like as you asked it?
Well, no, I'm just asking why it isn't considered a hydrogen bond, it's a bond with hydrogen.
Oh, gotcha. I know, I honestly wish they would have given it a different name for that intermolecular force. Because I feel like it makes it confusing, because number one, we use the word bond, when it's really not a bond, right? Like, and then other things can be connected to hydrogen and not have it. I wish they just called it like the super dipole or something like that. So, yeah, Miriam.
Could we start a petition to rename it like hydrogen friendship or something?
Yes, let's try. Let's contact, I don't know who we contact for that, but yeah, Marilyn.
So it says something around here that hydrogen must be directly bonded to NO or F to be a hydrogen bond.
Uh-huh.
Is that it?
Yes.
Okay.
Yep. So that's like the other ones, like carbon to hydrogen doesn't count. So, questions on that example of an FRQ? Okay, sorry I'm pushing us a little bit. I just want to get at least a few demos in today before we run out of work and time. Okay, our last property here is the property of dissolving or mixing. In terms of what they do, the reason is the same. The different use of word is really just a matter of what's combining. Okay, so solubility is used for a solid in a liquid. Okay, so we say salt is soluble in water. When you're talking about two liquids mixing, we don't really say they're soluble, we say they're miscible. That's what this word is here. But the Y is the same, just kind of two vocab words. If it's a liquid-liquid mixture, you call them miscible or immiscible. If it's a solid and liquid, then you call it soluble or insoluble. Okay? Now, our reason why for this one isn't, all our others we talked about so far were like a comparison of strength, right? Like, if it has high IMFs, then it has a high boiling point. If it has high IMFs, then it's going to have low vapor pressure, right? It's about the strength of it. To mix or dissolve isn't about strength so much as it is similarities. Things with similar properties will dissolve things with similar properties. So a polar substance can dissolve other polar substances. While if it's a non-polar substance, it won't dissolve or mix with polar substances. Yeah, Cameron.
So if oil is a non-polar molecule and it does not dissolve or mix with polar substances, does it mix with non-polar substances or does it not mix at all?
Yes. So non-polar will mix with non-polar. Yep.
That's like why soap works, right? Because soaps have a non-polar end and a polar end.
Yeah, so soap's a really cool structure because it's really big and one side is non-polar, has a big long non-polar tail. I think it's the tail's non-polar. And then the head is polar, and so it can attach oil and water to get yourself clean. Yeah, good connection, Gavin. Okay, questions on that idea of dissolving or mixing? Okay, one more practice problem here. You can talk with your table about it. Oh, first, read my comment. It's not really mine. I didn't make that. But if you laugh at it, then it's a good sign you're understanding. Thanks for the pity there, Grayson. You get it? Right? You get it. Even if you don't think it's that much. Yeah,
It's very corny.
it's a polar bear.
Just wait
And
till
he's in
the back one falls.
Polar water. Right? Polar dissolves polar. There's kind of, I would never use this as your FRQ justification, but if like a catchphrase we use in chemistry is like dissolves like. Polar dissolves polar, non-polar dissolves non-polar. Okay, I think once again about the friendship force. Okay, if you come in contact with someone else who has similar properties and likes to you, you often become friends really quick because you have similarities, right? Versus if you come across someone who doesn't have as many similarities as you, then you're less likely to mix. Okay? All right, last question here. Which of the following substances is going to be the least soluble in water between these three? And then which one would be the most? Okay, ready, set, go.
But how to draw a water bottle? How it interacts with
Yeah, it's not the same.
So look at their INS.
This one has more items.
Okay, that makes sense.
Why did you do that?
Is this how you draw it?
Did you get this part? Did you get this part?
Typically, yes. Otherwise, we'd use the term miscible, but yeah, in terms of like vocab use. Okay, I'm gonna number them so we can vote. This is number 1, this is number 2, this is number 3. Show me on your fingers, 1, 2, or 3. What do we pick here? Number 1 would be the least soluble in water. Why? It's non-polar, right? Okay, good. All right, number 2. Tell me what you put. Which one would be the most soluble in water? 1, 2, or 3? You probably don't pick 1 because we already said it was not that. Correct answer is 3. So why would this be more soluble than this, AJ?
Because the OH creates a hydrogen bond, which is a lot more polar than fluorine.
This isn't a hydrogen bond because it's not connected to an H. It is fluorine.
What do you mean by hydrogen?
Why does a hydrogen bond matter?
Yeah.
So a hydrogen bond is a stronger connection
And a polar.
than a polar bond. So this would dissolve, okay? I'm not saying it wouldn't dissolve, but this would dissolve more due to the hydrogen bond connection. Okay? The way we would show that is there's actually 2 places it could. So we draw a dashed line here. Now this is the positive end, so we need to connect it to the negative end of our water. So that's how it would look, something like that. Or technically you could have another one here, but that would then connect to the positive side of the water.
And why does that?
So your statement behind this is hydrogen bond has more polarity?
Yeah, because it's a stronger shift, right? You have a bigger positive and a bigger negative. So that's kind of what I was saying, Will, of like why hydrogen bond is a hydrogen bond. That's why I said it should just be called a super dipole, because that's what a hydrogen bond is. And so if you have a bigger positive and a bigger negative, then they're going to link up faster than like less magnitude of positive and negative.
So you're saying between oxygen and hydrogen because it's bigger, attraction is right or easier,
Yeah, so like this is a bigger plus and minus
or attracts
than the plus and minus that's there. Alright, this would still be negative, and this would be positive, but it's not as strong of a difference, I guess. So,
Oh, that's very.
once again, like dissolves like. If it has hydrogen bonding, then things with other hydrogen bonding would dissolve well. Yeah.
So is CH3OH a polar molecule?
Say that again.
Is it a polar molecule?
Yeah.
It
This
is?
one. Is that
No,
what
the
you
one. No, the one before. That one.
said? Yes, this is polar.
Well, I thought because it's like squished in between, it wouldn't be polar. I thought it has to be like one distinct side and another distinct
Well,
side.
it's also not drawn because it's like this one.
Oh,
actually
because it would be like.
bent.
Yeah, that
And
makes
so
sense.
you have like your negative here and then your positive there.
Okay, yeah.
Yeah, it gets tricky to visualize in 3D space when they get big.
Okay.
Another good connection information that I'm glad you asked this, you can't have hydrogen bonding and not be polar. Because if hydrogen bonding is a super dipole, there has to be a dipole. So that can be a nice thing is if you identify hydrogen bonding, it has to be polar. So, yes, you took your hand down. Do you still have a question?
Well, but doesn't it make it not polar because the oxygen takes both of the electrons, so it kind of like cancels out the arrows? And then
But it's not linear, that's the problem, right? It's not, the arrows aren't like
Yeah, yeah.
this.
Blue bend.
Oh,
bent.
okay, that makes more sense.
Yeah, the lone pairs make it better. Yes,
Bend.
Did we get a science about that one?
yes, have a smoke as you get that. Okay, turn to page, Seth, what page is that? 24 in your lab book. We won't finish them all, but let's do a few demos before we leave today. Don't let me forget, we need to turn in our smiley face papers today too, by the way.